cross-ply laminates, and about the influence of the residual thermal stresses, and we will apply a couple criterion to predict concept of crack in the transfer in the inner transverse laminate. As is well known, unidirectional fiber laminate has a high strength in the fiber direction and a low strength under transfer direction, especially in cross-ply laminates, especially the typical inner plies or transfers from 90-degree plies are subjected to transverse load around the first which fail. This is the well-known situation. Actually, this morning Dominic talked about the surprising size effect. It can be observed if you look for the critical strain, longitudinal strain, which leads to the appearance of the crack in the inner 90-degree ply. This size effect cannot be explained by classical fracture mechanics. For this reason, we will apply the couple criterion in this work. We see the size effect, the critical strength, as a function of the transverse ply sequence. However, residual thermal stresses in cross-ply laminate can be very relevant due to the classical use of the thermoset resin, and also because the high contrast between value of the coefficient of the thermal expansion in the direction longitudinal to the fibers and perpendicular to the fibers. For example, carbon epoxy laminate, the residual thermal stresses can achieve almost half of the transfer strength. However, residual thermal stresses are usually neglected in majority of criteria trying with this size effect observed by experimental fabrics. Actually, this presentation will be divided in two parts. In the first part, I will summarize the application of the couple criterion to this problem, and in the second part, I will try to explain why the agreement or coincidence we observe between dimensionless energy release rate in an elastic problem. First, let's look for the application of the couple criterion to this problem. The original problem we consider that we have 0-90-0-degree laminate subjected to some thermal decrement. This thermal decrement typically corresponds to the last stage of the cooling procedure in the autoclave, decreasing of the temperature, for example, from 170 degree to about 20 degrees. Decrement is usually about 155 degrees, for example, and also to some imposed longitudinal strain. And the question is when the crack will appear in this inner 90-degree laminate. Try to obtain a good agreement with experiment. As I mentioned, we will apply the couple criterion, which has been explained several times today, which requires the simultaneous fulfillment of the stress criterion. In our case, the transverse stress in the inner ply must exceed the transverse strength of the inner ply, 90-degree ply, in the whole region where the crack appears because of the uniform stresses. It is actually in the whole sequence of the inner ply. And these stresses can be computed by the laminate theory. I should mention that all calculations were carried out in this work by Professor García, in this work. And the energy criterion requires that the energy released during the crack onset must exceed the energy dissipated. Of course, this energy really should be computed numerically, and we use the Van code, but of course also final code could be used. Let's first look how the stress criterion is applied. This is the original problem. We have laminate without crack. We have the temperature decrement, and we have this applied longitudinal strain, which is the sum of the epsilon y is the external applied strain, and epsilon delta t is the longitudinal strain due to the this thermal decrement, temperature decrement. This problem can be obtained like superposition of the epsilon problem, where we have just applied longitudinal strain, a very longitudinal strain, and the delta t problem, where we have applied the temperature decrement delta t, but we have zero average longitudinal strain. If we look on the inner ply, the stress sigma y in this longitudinal direction can be in the global problem, can be obtained by the sum of the stress in the epsilon problem plus stress in the delta t problem. And due to the stress criterion, it should be larger. The stress in the global problem should be larger than the transfer strength of the inner lines. We can compute the stresses by the laminate theory and dimensional analysis. This was done by Israel. And here are the values. These parameters, dimensional parameter K, can be explicit expressions. They are lengthy, can be found in our joint publication in the International Journal of Science. Then, if we sum these two expressions, we can reorganize it a bit, and we obtain this form of the stress criterion, where longitudinal applied strain, this is the critical transverse strain, should be larger than this parameter E22. E22 this tilde is the apparent Young modulus in the inner lamina, and this is the term which appears due to the temperature decrement. Because this term is generally positive, then we will have here that actually the temperature decrement produces the decrease in the predicted critical strain by the stress criterion. If you look on the energy criterion, this is the formulation that the decrement of the potential energy should be larger than the dissipated energy, as proposed by many. And here again we consider superposition of the of two problems, epsilon problem and delta t problem, like the previous one, the stress criterion, but in this case we consider a crack of a length A. This length A is not necessarily the full thickness of the inner lamina, it can be smaller, and sometimes we observe that the optimum size is smaller than the full thickness of the inner lamina. We can of course use superposition of the stress intensity factor K1 in the problem epsilon problem and delta T problem. This partial problem can be solved numerically. We use the boundary method, which is very suitable for this calculation. And the G in the global problem, which includes both the decrement of the temperature and the applied longitudinal strain, we obtain actually this is a superposition of stress intensity factor by written in terms of the energy release rate, which typically are used in the composite community. Because of this, we have these square roots here. We normalized by the value of the transverse stress inside the inner ply in the anchor state. And we were surprised that this G epsilon hat and G delta T hat, which are these dimensionless energy release rate, we put here this dimensionless energy rate as a function of the length, semi-length of the transverse crack in the inner 90-degree lamina. We observe almost excellent, almost perfect coincidence. This is the percentage of the difference. It means because basically the numerical difference. It means because a surprise for us that we observe that these two energy release rate in the epsilon problem, which is purely a mechanical problem, and the thermoelastic problem delta T, they are coincident. Okay, and I will come back to this question in the second half of the presentation. Just if we rewrite this previous, if we use this energy release rate expression in this energy condition, and reorganizing, putting all terms with delta temperature decrement together, we obtain this formulation of the energy criterion for this problem, where gamma is the dimensionless brittleness number for this problem, and G is the dimensionless function, which where we have here the dimensionless increment of the size of the crack in the inner lamina, and this is the dimensionless decrement of the potential energy. If we don't have delta T, we don't consider thermal stresses, then this reduces to the expression we published in 2014. If we put together both criteria, stress criterion and energy criterion, we can observe that this additional term is the same in both criteria. It means if we combine these two criteria, which should be fulfilled simultaneously, we arrive to this expression where we have minimized with respect to length of the crack, the inner lamina in the onset of this crack. Here we have everything is dimensionless expression, and this term can be written as the ratio of the residual elastic strain associated to residual thermal stresses and the critical transverse strain. Applying this criterion, we obtain this prediction for zero temperature decrement, which we observe this is basically the stress criterion governed region, and this is the energy criterion governed region. But if we consider decrement in the cooling down stage of the curing process in the autoclave, we observe the big difference in the critical strain is obtained. Actually, if we don't consider these thermal stresses, we are overestimating a lot the critical longitudinal strain in this cross-ply lamina. If we consider this real temperature decrement, this is the theoretical prediction by the Kappa criterion, and these are a result of we obtained in our laboratory. And the blue circles are first crack onset observed by acoustic emissions, and these red squares are the first simultaneous crack onset, and we obtained very good agreement. Imagine if we wouldn't use this, we wouldn't consider this thermal temperature decrement, the prediction would be totally out of the experimental observation. Coming back now to the question why these energy release rates as function of the crack length in the inner ply are equal. Okay? And we will try to explain it using the Shelby procedure, which is called sometimes cutting, deforming, and gluing procedure. In this sense, we will first consider all these laminates like independently deformed by temperature decrement delta T, and of course they become incompatible. We cannot glue them because one is shorter and other is more larger depth. In order to make them compatible and then we can glue them, we need to apply, in this case, uniform stresses in the longitudinal and let's say in the y direction, and this in the zeta direction. In this, we apply these stresses, which will allow us to obtain the same strain in the 0 degree lamina like in the inner 90-degree lamina. Even if we have crack here, but there is no energy release rate in this problem because 0 degree lamina, sorry, 90-degree lamina is under zero stress. Okay? It is just freely deformed because of the temperature factor. We combine this problem P1 with another problem P2, where we have a cross-ply laminate. Now we have bonded plies under imposed strain epsilon 1 and epsilon 2 in the problem P2 in the way that the total forces or resultant forces in the y direction, in the zeta direction, are opposite in the resultant forces in the previous problem, where we apply forces in this axial forces in this 0 degree lamina. Okay, then we apply here the forces of the same value on the opposite side. If we now go to the superposition of these two problems, Of course, in this problem we have no energy release rate. Energy rate in the problem T2 should be computed numerically. We did it using boundary element code. And if we make a superposition, we obtain the thermoelastic just the thermoelastic problem, because we have temperature decrement, but we don't impose any external strain. And because energy release rate here is 0, it means energy release rate in this situation is the same as in the problem P2, which is purely elastic. But we can question if in this problem, because we are applying also axial forces in the zeta direction, if energy release rate, the variation is the same like in the purely elastic problem. You can easily show in this scheme if we make the superposition with another problem P3, where we just apply the axial axis in the zeta direction, sorry, external force in the zeta direction is the opposite sign like in this problem, and in the y direction we apply another force, of course uniform strain, which lets this inner ply under 0 stress sigma 1. In this sense, we will have here no energy release rate, K1 will be 0, and this is actually a kind of epsilon problem. And the energy release rate in this problem is the same, and in this sense also the problem in the thermoelastic problem is the same like in the elastic epsilon problem. We have shown that the energy release rate variations, dimensional energy rate variations are the same in the thermoelastic and the elastic problem, because we have applied the Capra criterion to the problem of crack concepts in 0-90 degree cross-ply laminates. We obtained excellent agreement with experiments, and we also explained using Eshelby procedure why the variation of normalized energy release rate in the thermoelastic and the elastic problems are the same. Thank you for your attention.
Thank you.